Hello, everyone. Good morning. My name is Guan Le. I'm from Institute of Information and Engineering, Chinese Academy of Sciences. This is a joint work with my advisor, Professor Lin Jinqiang, Professor Jin Jiwu, and Professor Luo Bo from the University of Kansas. Today, I'm going to talk about a technique that takes advantage of a hardware feature in modern processors to protect private keys. Private keys are widely used in electronic commerce activities. For example, it can be used to identify the ownership of websites. It can be protected through theoretical ways, such as threshold cryptography, leakage resilient cryptography, etc. But in practical applications, before it can be used to do cryptographic operations, it must first be loaded in the RAM as a whole in plain text. On the other hand, we must also guarantee the confidentiality of it. Unfortunately, a memory disclosure attack allows an attacker to read unauthorized data in RAM, which may include the plain text private keys. This kind of attack is very powerful in that it does not compromise the code integrity. It just steals data silently. And it does not assume any specific vulnerability. It can use buffer overflow, type error, etc. Everything. So existing defending technologies such as DAP, ASLR are all inefficient. For example, the infamous OpenSSL heartbleed bug allows an attacker to overread sensitive context. This, according to a statistic, this kind of attack contributes about 16% of all the Linux kernel vulnerability. And when we click into the column in red with the header gain information, we can see that almost all of them allows an attacker to steal some data from kernel space. And so, how to keep private key secret under memory disclosure attack is a big challenge. Here we propose Mimosa that aims to erase sensitive data whenever any other process attempts to read them. We make an analogy here. There is a plant called Mimosa that protects itself by folding its folders when touched or shaken. And similarly, Mimosa protects private key by erasing them when attack is detected. Our goal here is, of course, to detect and prevent such attacks with no delay or false negative. Otherwise, the key would have been stolen. Before we talk about the technical details of our solution, let's first talk about some technical background. In multi-threaded programming, shared data often lead to data consistency. As a traditional way as a typical solution, a programmer needs to declare a critical region and require or release the lock when entering or exiting the region. But the result is that all the code that may potentially access the shared code will be serialized. This is a big performance overhead, especially for multi-core systems. To speed up multi-threaded program, transactional memory was introduced. Transactional memory allows for speculative multi-threading. That is, all the threads just execute in its own path simultaneously, and only if a real data conflict detected did they roll back to a checkpoint. To implement the transactional memory, there must be mechanism to track data accesses to detect future conflicts, and when a real conflict happens, there must be a mechanism to roll back. Transactional memory can either be implemented in software or hardware. In a hardware transactional memory, we mean the processor has architecture support for the above-mentioned mechanisms. This includes tracking, conflict detecting, and rollback. Now let's go back to our system. The basic idea of our system is to implement cryptography as a transaction. And if there is no cryptographic request in the system, the key just reside in RAM as as a ciphertext. The key to encrypt the private key is stored in a privileged register. And to this end, we employ Tracer, a memoryless encryption solution for AES. And when there is a cryptographic operation request, the key is decrypted on the fly inside the transaction memory. And sorry. And after the cryptographic operation and before the result is committed, we must manually erase or clean the private key and all the intermediate sensitive data. If somehow a malicious thread want to attack, have some privilege to access the plaintext key inside the transaction memory because of the nature of transaction memory, the transaction will be aborted, and all the intermediate sensitive data will be cleaned automatically. To better understand our solution, let's look at this figure. On the left side is the mimosa thread, and the right side is the malicious thread. Mimosa thread begins with xBegin, which is an instruction that marks the beginning of the transaction memory. From that time on, the data is tracked in processor. In the third step of Mimosa, the private key is generated on the fly and written to the memory. The first four steps in malicious thread are all benign, but the last one want to read the plaintext private key. And this, because of the nature of transaction memory, this will cause data confliction, and the transaction memory, the transaction will abort. Thus, the last step in Mimosa thread cannot go on, and the sensitive data is erased by the hardware automatically. So the result is that the attacker cannot get the plaintext key. And specifically, we employ entire hardware transaction memory to implement our solution. So there will be no delay or false negative. There is a side benefit of our solution. Because almost all the commercial hardware transaction memory implemented inside the processor support data tracker inside their on-chip cache. Because the private key is generated on the fly, so they will appear nowhere other than the cache. In other words, our solution is immune to some physical attacks targeting DRAM, such as code boot attack. As mentioned earlier, our solution guarantees the confidentiality of private key, that is with no false negative. But in an IDS system, we know that low false negative often leads to high false positive. A high false positive means that the transaction is about again and again, and there will be no availability at all. And in other words, the solution may have performance impact. And it turned out that we have a very rough start. In our naive implementation, we write a simple code to do cryptographic operations inside the transaction memory until there is a successive comment. But unfortunately, the thread stuck forever. That is, it aborts again and again. That is 100% false positive. Note that this is even under no attack scenario. So we have to do many performance trainings here. Firstly, we eliminated the use of instructions that is incompatible with transaction memory. We identify them and replace them with alternatives. Second, we must avoid data sharing caused by Mimosa itself. This includes true data sharing, which happens when some data is really shared by Mimosa. So, for example, the location library. And This includes false data sharing, which happens when two Mimosa threads access two different memory locations that happens to be in one cache line. And the fourth one is that the RC computation usually takes a very long time, during which the transaction may be interrupted. So we temporarily disable the interrupt during transaction. And finally, we delayed for several CPU cycles after continuous abort. This is also recommended in almost all the commercial hardware transaction memory manufacturers. And the final result is that we achieve the abort cycle ratio is as low as 5% under no attack. That is, we waste about 5% CPU cycles. And we have implemented our prototype inside the Linux kernel and provide a security-enhanced RC service through system calls. And we further encapsulate it inside an OpenSSL engine to make it easier for Mimosa to be integrated in other applications. To measure the performance of it, in real-world applications, we integrate Mimosa to the Apache web server and measured the HTTPS throughput. We compared Mimosa with official Polar SSL and Mimosa no HTM, which is the same as Mimosa, but with hardware transaction memory disabled. We can see in the figure that all the three solutions are very close with each other in terms of HTTPS throughput. And end-to-end latency is also a very important metric in web service. So we measured the 95% percentile using Apache benchmark. We can see that when the concurrent level is low, all the three solutions, the performance are very close with each other. But when the concurrent level goes higher, we find that the gap between them becomes larger and larger. So we recommend to only use Mimosa in low or medium workload. To conclude, we use a hardware feature to protect private keys against software memory disclosure attack with no false negative. And because of the nature of transaction memory and because of the nature of our solution, the plain text private key will never be loaded to the DRAM chip. So our solution is also immune to some physical attacks against the DRAM chip. This includes code boot attack, bus monitoring, DMA attack, etc. And through our evaluation, we found that the performance of our solution is very close with open source packages. And through our experience in designing and implementing our solution, we demonstrated that advances in computing can also boost the security. Thank you for listening. I will be glad to answer your questions. Thank you.
Thanks a lot, Leguan. Any questions from the audience? Yes. Ian. Could you introduce yourself?
Hi, Ian Goldberg, University of Waterloo. Feedback. So you said you had to disable interrupts.
Yes.
So for a non-trivial amount of time. So what goes wrong with the rest of the system while interrupts are disabled?
Yes, we disable the interrupt temporarily during each transaction memory. And the result is very bad because it influences the end-to-end latency as demonstrated earlier in the figure.
Right, but what about all the rest of the stuff the system's doing that needs interrupts to happen, like network packets arriving and...
Yes, it cannot handle the interrupt in timely. But we have multi-core here, so maybe another core may handle it.
Okay, thank you.
Any other questions? I have a question about what you have mentioned with performance tuning. You had something on the slide mentioning that you were doing an optimal empirical analysis. So I was wondering, based on how many experiments were these, optimality? Yeah,
The fifth one.
yeah, the fifth one.
There is another paper that is written by Intel engineering, and they have some statistics, and we also proved it with our experiments. Yes, and we adjust. We adjust the delayed cycles ranging from, for example, 10 to 1,000, and find the one that with the best performance. And maybe this parameter may change across platforms. Yes.
Yeah, so that's why, I was wondering, if I change my platform, how would I be able to use it?
Yes, this is a problem.
So I was just wondering if I change my platform, the optimality, I have to basically.
Yes, because this hardware feature is ongoing work. Last year, there is a bug in the Intel chip, and they disabled this feature temporarily, and now it's opened again. So it's not very. Yes.
Okay. And I have another question. So for the workload experiments that you had at the end, how many benchmark did you run for the results that you were showing?
We run 10,000 requests. Yes, during under different contract levels.
All right. And you mentioned the ongoing work with the more intensive workloads to make sure that you can handle those using low overhead at the end.
Yes, when the contract level is higher, the end-to-end latency will be high in web services, because we disable the interrupt. Maybe this is a bad impact.
Okay.
Actually,
Thanks.
I have a
Oh,
question.
yes.
Okay. Jufeng from Columbia University. To understand that whenever there is a conflict, hardware would roll back the memory updates. I'm just wondering if the malicious thread can actually read the key before the hardware update happens, because the malicious thread is not running within a transaction.
Yes. Here, the private key is decrypted on the fly. If there is outside the transaction memory, the private key is residing in RAM as ciphertext.
Okay, so before you start a transaction, is encrypted, and whenever you start a transaction, you decrypt it, but you don't write it to the memory?
Yes.
You do not write it to memory, right? Okay, all right.
Okay. Thanks, Logwan.